Good afternoon, everyone. Thanks for coming to our session. My name is Yiming. I'm currently a postdoc at UT, and today I'm very happy to be here to talk about our recent work in LLM-powered digital twin for interactive urban mobility simulation. Before getting into details, I want to acknowledge our team behind this work, including our team leader, Dr. Junfeng Jiao, our postdoctoral fellow, Dr. Kijun Song, and our research assistant, Mr. Jiang Park. And to better understand our motivation and the background of our research, I want to firstly to introduce some basic concept about related to the urban digital twins. So the urban digital twin is interactive data. Urban digital twin is an integrated data-driven virtual representation of a city to simulate, analyze, and predict real-world urban scenarios and dynamics. As we can see from the figure, the digital twin is constructed based on the data from the real world, which is a physical twin, and the digital twin conducts the simulation, analysis, and prediction to help in decision making of the real world. And the previous study has showed that the digital twin can help in efficient city monitoring, optimal policy making, better resource allocation, and effective management. So to achieve this, the digital twin should have multiple functions, including the virtual world that visualizes the city, the data hub that manages and integrates data from different sources, the city monitoring that enables real-time awareness, and the prediction and the simulation to model the future of the city dynamics, and the smart assistant that help the planners to make decisions. And in addition to this, there can be a stack of machine learning technologies integrated into this digital twin framework. For example, the deep learning that can help in the prediction, the reinforcement learning method that can help in infrastructure optimization, and the computer vision that can help in city monitoring and so on. So specifically, an urban digital twin can include different data layers, such as the terrain layer at the bottom, the material layer, the land use layer, the utility layer, infrastructure layer, and so on. However, the stakeholders cannot directly use this data for their purpose. So we have to select some specific data layers and combine them together and integrate some tools like AI tools or some method to generate applications for their use. And these applications can serve the needs of the stakeholders, and we can also get some feedback from the stakeholder to generate new applications and improve the existing applications. So, for example, the transportation system application it's based on the terrain layer, the land use layer, the infrastructure layer, the mobility layer, and the energy layer. So, based on these layers, the transportation system application can conduct the data analytics and the simulations to get some historical patterns and insight and future insights for the stakeholders to help them to better planning and manage to better plan and manage the city. And in this application, the simulation is very important. It's very important for us to test the what-if scenario. What if scenario to know the future and to help the stakeholder to enhance their planning strategy or their management strategy. So in the following slides, I will dive into this part of the digital twin, which is a tool we developed named LLM-Powered digital twin for transportation simulation. So basically, transportation simulation is a mathematical and computer-based model of transportation systems. So there is several transportation simulation platforms available in the market, such as SUMO, the PTV Visum, the Transmodular, and so on. Although these transportation simulation platforms have different features, their simulation process is quite similar in general. You can see from the figure that firstly you have to install the software to your computer and set up the environment in your local environment, and then you have to collect the data of the road network and generate and build the road network with edges and nodes in your software, and to create the network in the simulation software. Then you have to determine the number of trips between different areas to determine the origin and the destination flow between different areas, and you have to determine the route and the travel mode of each trip. After that, you can conduct the simulation based on the things you have. However, there are usability gaps in current transportation simulation softwares. So these transportation simulation softwares are unfriendly to new users, and the learning curve is very steep. So if you want to run simulation, you have to be familiar with the environment setting of the operating system. You have to be familiar with the command line, the configuration, and you have to build the road network in your software. And you have to set up the demand, the routing, the traffic lights, and so on. And in addition, you have to, before running a simulation, you have to read the user documentation, and which can be 80 pages long. So how can we deal with this problem? And how can we make the transportation simulation more accessible to new users? And our solution is agent. So we want to create an agent that can understand the command of a user and conduct the transportation simulation automatically. And we also want the agent to answer some general questions regarding the simulation and help us to analyze the simulation results after the simulation. So to do this, we developed an LLM-powered digital twin for transportation simulation. We use the SUMO, which is the open source transportation simulation platform, as our engine, and we developed a Python script and use the OpenAI agent SDK as our backend, and we developed a web front end using the JavaScript. And the agent is connected to the SUMO using the Python tools we developed, and the agent is also connected to some third-party tools like the Google Maps using the MCP. So here is a demonstration of this platform, and we can see that there is a chat box that enables the interaction between the agent and the user, and there is a base map that visualizes the location of the vehicles, and there is also some control panel so that we can control the simulation manually. And there is also a dashboard to display the simulation status in real time. And the prompt I use in this demonstration is listed in the right. And firstly, I asked 2 questions regarding the simulation and the platform, and then I asked the agent to run simulation with some specific configuration, and then I asked the agent to stop the current simulation and run another simulation with other configurations. And you can see that the agent just followed my command, and it can stop the simulation, and it can run simulation with different configuration. And after these 2 rounds of the simulation, I asked the agent to compare the result of the 2 simulations, and it can also give the right answer based on it can automatically analyze the results of the simulation and give some metrics of the simulation and provide some results. And at last, I asked the agent to provide some suggestions to improve the traffic based on the 2 rounds of the simulation. And it can also give some reasonable and insightful suggestions for us. So we also connect. I cannot play this video. Okay. We also connect our. We also connect our digital twin to our 3D city model, so that to enhance the spatial understanding of the simulation. And the combination is showing actually in a right video, but it cannot play here. But I can introduce. We conducted a co-simulation between the SUMO simulation and the Omniverse 3D model, so that we can get some spatial understanding and get some like first person view from the vehicles. So it is very useful for currently for autonomous vehicle driving, for example. So we developed this simulation platform to solve real world problems. So here is a use case for this platform in the travel time estimation for the emergency medical service vehicles. As you can see from the video, the traffic and the infrastructure can cause some delays for the EMS vehicles, and the delays will vary across different road segments. So our research question in this application is to estimate the travel time delay on each road segment for the EMS vehicles. So specifically, we have some empirical trips for the EMS vehicles, and based on this data, we conduct the simulation with a free flow scenario using our digital twin. So this scenario will generate the minimize the minimum travel time for the EMS vehicles for each trip. So when we compare the ground truth trip duration and the simulated trip duration, we can get the delay for the whole trip. However, the trip is combined. The trip includes different road segments. So we have to assign we have to develop a model to assign the delay to each road segment. So this problem is challenging because we only know the trip level delay, and we don't know the road segment level delay, and also the data is sparse, and there also and the delay is spatial temporal difference. So to deal with this problem, we developed a model named, which is a physics-informed neural network model to deal with this problem. So besides the simulation, the dual tone also provides some data about the road infrastructure information, including some the edge length, the speed limits, and the number of lanes for the road segment. Then we also include some the temporal information in this model and embedded it in our model. And after we use MLP to process the embeddings and get the road segment level delay, and then we combine this together to get the trip delay and predicted trip delay and compare it with the ground truth trip delay to get the loss, so that we can optimize the parameter in the MLP. So now here's the case study in Austin, and in this case study we have over 188,000 EMS trips. And we extracted the whole road network for the city of Austin, which includes over 98,000 edges. And we can the destinations of the EMS trips are displayed in the middle finger, and the distribution of the edges is displayed in the right finger. So here is the result for this case study. The edge delay for the whole city of Austin is displayed in the right finger, and for the middle and the right finger, we display the edge delay in the Austin downtown area at 9 a.m. and 5 p.m. And this pattern is consistent with real-world transportation system operations. So, for example, we can look at the blue boxes. This is a MOPAC northbound highway, and we can see that the delay in this area is higher at 5 p.m., which is consistent with our experience. So there's a lot of traffic in this area during around the 5 p.m., and heavier traffic will cause more delays in this area. And this result can help the cities to generate the optimal route for the EMS vehicles to better save lives, and also can help us to provide some proofs for the cities to improve the infrastructures of the transportation network. So at last, I want to thank our partner for their support to our project. And thank you for your attention, and I'm open to questions now.
Questions? Yes?
Thank you. So what is the single most important leverage that we have to improve the speed of traveling between origin and destination? Is there any way in which you can actually optimize for that in the city?
I think we can only optimize this from two aspects. Firstly, to improve the infrastructure, to increase the speed, operation speed, and reduce the delay. Another thing is that if we can, this is a long-term plan for the cities, and for the short-term plan, we can generate the shortest path with the minimum delay for the EMS vehicles, so that it can reduce the travel time based on the results. Any follow-up?
So is there no alternative to the infrastructure? Because usually you find that the more the infrastructure, the more the traffic jams.
This is a good question. However, the traffic pattern also, besides the infrastructure itself, the traffic pattern is also determined by the demand, traffic demand. So, for example, at 5 p.m., there will be a lot of traffic, like from the downtown Austin to the rural areas. So this is also like this demand will also affect the traffic itself. So this is a complex problem. So what we can do is to find the delay and get the optimal trip right now.
So this doesn't explore network optimization?
No.
Would that be one way to?
Yes, yes, exactly. Yeah.
I have a question. What experimentation have you done to show how well your predictive model works with the actual observed data?
Oh, we just evaluate the model accuracy based on our data with the chip. We only have the chip level data, so we evaluate the error of our model with the validation with the empirical chip data to get the error. So the error itself, the goodness the accuracy is the MSE is about 80 seconds, and the RMSE is below 100 seconds. Yeah.
So if you looked at new trick data, so you kind of said, well, here's my training, validation, testing, and now I have new data coming in. If you looked at that.
So we actually divide our data into a test set and a training set. So no, our model didn't see the data in the test set, so we can validate that our model works in the new data. Yeah. Thank you.
Yiming, can you talk about, imagine about how the true agentic model can improve the traffic simulation? Think about Cloudbot, although fully autonomous agent like us.
Yes. So I think there is a very popular tools recently called the Open Cloud. So this our agent we have is very similar to this Open Cloud, but with specific application in transportation simulation. So our agent can fully handle the whole simulation system. It can terminate the simulation. It can adjust the configurations in real time, and it can also close specific road segments or adjust the traffic light in real time. So I'm very happy to see that there is this kind of tools to help us to improve the accessibility of the transportation simulation, which is very important and useful for the cities to optimize their transportation planning and management. Yeah.
If there aren't any other questions, we'll take a brief pause before our third and final talk, which starts at 3:10. Thank you. Thank you, Yiming.